Hello everyone, I am Dr. S. Shashi Devi, Associate Professor of Physics working in Vardhaman College of Engineering.
In this session, we are going to discuss about the black body. What exactly the black body radiation is? What exactly a black body is? A black body is that body which is going to absorb all the wavelengths and emits all the types of radiation. So it could be any body. So there is no specific that this could be a black body or something like that. So any body can be act as a black body. For example, let us suppose that this is a black body. First, on this black body, let me incident some radiation. I am going to incident some radiation on this black body. What is going to happen? Once the radiation falls on this black body is going to absorb all the radiation, and at the same time, this black body also emits the radiation whatever it is absorbed. And this radiated emission is in the form of thermal energy. It means, what is a black body? A black body is a body which is going to absorb all the electromagnetic radiation which is going to fall on a body, and as well as at the same time, after absorbing, this particular body is going to emit all the radiation. Okay, fine. Then, what is the difficulty in this? So, this black body radiation experiment was done at the early stages of 20th century, that is in the 1900th century. But the major difficulty in this experiment was the classical mechanics could not able to explain the graph drawn by this particular by using this black body experiment. Why is it so? And who was the person behind to explain the black body radiation? For that, to draw the graph, here I am going to take a black body at 3 different temperatures. It means how this black body, the radiation emission depends on the temperature. For that, first let me take a black body, that is, to this particular black body I am going to give a heat energy of 900 K. A 900 K heat energy is given to the black body. Therefore, after absorbing this 900 K heat energy of this black body is going to emit the energy in the red light. Next, when the same black body, if I am going to give the heat energy of 1300 K, then this black body is going to emit the energy in the yellow light. Similarly, when the same black body, if it is given the 1600 K heat energy, if it is applied to this black body, then this black body is going to absorb all this energy and it is going to emit the energy in the form of blue light. Then what does it mean? It means the conclusion from this particular experiment is difference in temperature means difference in radiation. It means if I will take the different temperatures, here I am going to go on increasing the temperature. The temperature is not constant here. The temperature is keep on increasing. Okay. When the temperature is keep on increasing, it means the radiation emitted by this black body is different. It is not the same. It means the radiation changes with respect to the temperature. That is, difference in temperature means difference in radiation. Now, let me draw a graph. Now, here in this slide, I am going to show the graph between the wavelength emitted and the energy of radiation or the intensity of radiation or the wavelength, E versus lambda. I am going to draw a graph. Now, when you look into this graph, where you can able to see, at first, at 900 K, I am going to plot a graph, so which emits the red color, and at 1300 K, the same plot is going to release the yellow color, and at 1600 K, the same plot we are going to get a blue color. So, then what is the meaning of this? It means as the temperature is increasing, energy is also increases. As the temperature increases, energy also increasing. That is the first major point, the first major outcome of this experiment. That is, increase in temperature increases the energy of the radiation. And the second important point is, that is, increase in temperature increases the energy of radiation. And the second important point is, increase the temperature, that is, the wavelength is decreases. As the temperature increases, what is happening? The wavelength is also decreasing. And not only that, here you see there is some peak points. There are some peak points as well. You can able to see that there are some peak points are there. So these peak points are in the visible region. These peak points are in the visible region. It means visible region is that region where humans can see with the naked eye. So what are the colors we are able to see? So when we see the electromagnetic spectrum, in that all the radiation the humans can't see. So there are some shorter wavelength radiation is there are some longer wavelength radiations are there. That is, infrared radiation is there, radio waves are there, gamma waves are there, X-rays are there. These are all the waves we can't see. The only spectrum what humans can see is the visible spectrum. So these peak points, whatever we see here, so these peak points are in the visible region. Only we can see this. But after this, whatever the radiation is there, so this radiation is the infrared radiation. This is under the infrared radiation where humans can't see that. So this is what the spectrum obtained by the black body radiation. But what classical mechanics tells us? Classical mechanics tells us that the energy is released continuously. What the classical mechanics tells us? That the energy is released continuously. When it comes to the real, so here this graph both are not same. So this is what the classical mechanics, but here this is not what happening here, but here we got the peaks of light and here the energy is released, some discrete packets of energy, some packets of energy is released here. So where the classical mechanics failed to explain this, and this particular point was explained by the famous personality is that Planck's constant, Max Planck. Max Planck came into the picture to explain this black body radiation. So Max Planck explained the black body radiation in around 1900. In 1900, Max Planck wanted to explain this radiation produced by the black body. Because classical mechanics failed to explain this, Max Planck, he said that energy is not released continuously. He said rather the energy is released in the form of discrete energy is released. Discrete energy. Energy is released in the form of, and this discrete energy he called it as quanta of energy. Called it as what? Quanta of energy. And one quanta of energy is, he said, as h nu. One quanta of energy is nothing but the h nu, and he gave the famous equation as E is equals to h nu. So in around when? In around 1918. So started around 1900, and here he got the Nobel Prize in 1918 for the work whatever he did. So he got the Nobel Prize for this, and the famous equation he gave as E is equals to h nu, and this E is equals to h nu is known as one quanta of energy, and based on this particular quanta only a new physics was originated, and that physics is known as the quantum mechanics. That physics is nothing but the quantum mechanics. So then they thought that classical mechanics will not able to explain all the laws, all the particles behavior. So classical mechanics could successfully explain the macro particles but not the micro particles. For the micro particles we need one more theory. and that theory is nothing but the quantum mechanics. That is, he said that the energy is discontinuous. Energy is discontinuous. The energy is not continuous, but rather it is discontinuous. So, this is what the famous equation given by the Max Planck, which is known as E is equals to h nu. And based on this Planck's quantum theory, next Einstein applied, who came into the picture? So, next Einstein came into the picture and wanted to explain this photoelectric effect. Photoelectric effect. Einstein wanted to explain the photoelectric effect, because even this photoelectric effect was not explained by the classical mechanics, and Einstein wanted to explain the photoelectric effect by using the Max Planck's equation based on the postulates whatever given by the Max Planck. Now, let us discuss about the photoelectric effect. Thank you.